In this section, we are going to study the geometrical effects of arithmetic operations on two complex numbers. So basically, we are going to study how does arithmetic operations like plus, minus, times, divide changed the way my complex number looks like in the Argand diagram. So we are looking at changes in the Argand plane. So let us begin with a simple case. Suppose I have two complex numbers, z1 and z2, and they are expressed as such in polar and exponential form respectively. Then I know if I want to multiply the two of them, there will be some special properties on the modulus and the argument of the product. In fact, I know that the modulus of the product will be the product of the modulus of each of the complex numbers, while the argument of the product will be the sum of the arguments of z1 and z2, and therefore I can write down my new complex number which represents the product in this way. Now what is easily recognizable from this? I see that for r1 times of r2, this basically means that the new modulus would be either stretched or shortened depending on the value of r1 and r2, so this might be a little bit hard to interpret. But for theta 1 and theta 2, now this will be easier, and this is the property that we are going to focus on. So let's say my original complex number z1 was over here, and z2 was over here. So then this would be an angle of theta 1, and this red angle over here would be theta 2. So what would the argument of the new complex number be? It will therefore be theta 1 plus theta 2, so it means that it's going to be theta 2 added by another angle of theta 1. So therefore I know my new complex number z1, z2 will have an argument of this, which is theta 1 plus theta 2. Then what about the modulus of z1, z2? It will then be z1, the modulus of z1 times the modulus of z2. So it's going to be stretched and it's going to be longer. So I know z1, z2 will be something like this. Okay, so without knowing the exact values of z1 and z2, I am still able to deduce some geometrical relationship. This is further visible from the case where we do division, and it is actually quite similar, but now because of what we have studied on the properties of the argument, instead of taking the sum of the argument, I'm going to take the difference. So now I'm going to explain the difference using another diagram which has been printed over here. So suppose I have an angle theta 1 which is associated with the complex number z1, and I have another angle theta 2 which is associated with the complex number z2, and I want to find the argument of z1 over z2. And then I know it's going to be theta 1 minus theta 2, so the difference will be this small angle over here. Therefore, where would my complex number z1 over z2 lie? It will lie along this line, because this green angle and this green angle must be the same. Okay, so this would be the angle theta 1 minus theta 2. As to the length, it's going to be r1 divided by r2, so it's going to be shorter. And that's how I arrive at this. Without the precise values, it is difficult to obtain the exact value for the modulus, but in terms of the angle, we are still able to do some deductions. So in general, what we say is that the geometrical effect is a rotation as well as a scaling. So the rotation comes from the effect of the argument, while the scaling actually comes from the modulus. Okay, because we either multiply or divide the modulus, and it is a composition of these two because both will take place at the same time. So that was for the case of z1 times of z2. Now what if I have a special case? What if I want to find I times of z? Then the modulus I can see will remain unchanged, mainly because the modulus of I is 1. What about the argument? Well, I know the argument of I is pi over 2. So now this is going to be the same as adding 90 degrees to the original argument of z. So let's imagine, let's say z was originally here, with an angle of theta. Now if I were to add 90 degrees to this and yet still have the same length, I therefore know that IZ will be somewhere here. And these two lengths must be the same. So how can I describe this transformation? I can see that this is a 90 degrees anti-clockwise rotation of Z about the origin because I move this way. I will now pause for a while for you to consider the case of negative IZ. So try to draw a Argand diagram to explain this, and when you are done, continue with the next video.